In this video, we're going to do a full discussion of the Diels Alder reaction. There's a whole lot of detail to this, and it's a little bit complicated, but if you pay attention, I think you won't have any trouble with it. So the basic Diels Alder reaction is what we call a 2+4 reaction. An alkene reacts with a diene. 2 electrons here, 4 electrons there, 2+4. And of course, it's a simple cyclic process where we have 3 arrows showing the movement of the 6 electrons. So we form this nice cyclohexene ring. Now, the real question is what's the stereochemistry, what's the regiochemistry of this reaction? And that's what we're going to really explore in detail. So the 4 pi diene is that part, of course. And down here is the alkene we also call the dienophile, which means it's seeking a reaction with the diene. And to the essence, you can consider the dienophile as the electron donor in this reaction and the diene as the electron acceptor. Actually, there's electrons going both ways, but that's kind of the net effect. 2 new bonds are formed at once, and it's what we consider a concerted reaction because both bonds are formed at the same time. Now, the simplest Diels Alder reaction between butadiene and ethane is not very favorable. You have to go way at high temperature, 200 degrees, closed vessel, use pressure, and you can make it work. But how can you make it more favorable? Well, like with lots of reactions, this is essentially an acid-base reaction. And what we want to do is we want to make the base a better base. We want to make the acid a better acid. So how do we do that? Well, what we want to focus on is this HOMO-LUMO interaction right here. These are the highest electrons in here. This is essentially the base, and this is essentially the acid because it's the acceptor orbital. So that's the fundamental interaction that we're going to deal with. And so the base is the diene, the acid is the dienophile, the alkene. And what we're showing is that the electrons flow from this highest occupied MO on the diene into this empty orbital on the dienophile. Now, how can you make something a better base? Well, you make a better base by adding more electrons. So you want to raise that level, and the way you do that is putting on an electron donor group. Electron donor group will essentially put more electrons in the system, and the HOMO will go up in energy. And so, how do you turn around? How do you make something a better acid? Well, you do the opposite. You put on something which will lower that level, and what you do you do on an electron withdrawing group. So if electrons get up there, they'll be lower in energy, and this will have the effect of again, lowering the gap between the HOMO and the LUMO where the reaction is taking place. So we want to remove electrons. We want an electron withdrawing group. Now it says remove electrons. There's no electrons in that orbital, but there will be once they're promoted. And so we're lowering the potential for electrons, if you will. Now, so we need electron donating groups on the diene, and we need electron withdrawing groups on the dienophile. So what's an electron donating group? Well, here I have 5 possible molecules. 4 of these electron donating groups. I set this up as a quiz. It's down below. So a methyl group, you maybe should do the quiz first before you hear me talk. So pause and answer the question. But let's go ahead and look at it. Well, what are the good electron donors? Good electron donors are things of lone pairs. Methoxy is a good electron donor. The acetate here is a good electron donor because, again, you have lone pairs in this oxygen. The amine is a great electron donor. So the B, C, and E would all be quite electron rich. Methyl is not a great electron donor, but can donate a little bit through hyperconjugation. And just a methyl group is enough, indeed, to increase the reaction rate. On the other hand, a carbonyl is an electron withdrawing group. So this one is not a donor at all. So A, B, and C, and E would be better dienes. The one with a carbonyl would be a worse diene for this reaction. So how do these electrons get donated? Well, you have your pair of electrons on your oxygen here, and you just shove them into the diene. And of course, what you do is you get a buildup of negative charge at the far end, which is kind of interesting. So the far end of the diene, away from the donor, gets some electron buildup. What if you put the oxygen not on a first position, but a second position? Of course, either second position will work. I'm picking this one down here because when those electrons go in, they end up on the same carbon down here. So the best of all positions would be to have a donor on carbon 1 and 3. That would make it a super good diene. If you start putting donors on all of the carbons, then it would become a very good diene, but there wouldn't be any directionality. We're going to see that there's directionality from the fact that there's a buildup of negative charge on this carbon in particular. So keep that in mind. This carbon here away, either on the opposite side of the donor or next to the donor, that particular carbon is going to get buildup of negative charge. So negative charge, that particular carbon atom. So let's look at electron withdrawing groups. Now we're going to look at the dienophile on the alkene. Which of these withdraw electrons? Well, obviously anything with a carbonyl withdraws electrons. So A is withdrawing electrons, B, C, and then the cyanide is good. Cyanide is not as good as carbonyl, but it's pretty good. So A, B, C, and E are good. On the other hand, this is an ester again, and that oxygen is donating electrons. So D is more electron rich. A, B, and C and E are electron poor. Those are electron withdrawing groups. So A, B, C, and E would be good dienophiles. D would be a horrible dienophile. So again, we're looking for electron withdrawing group. And now resonance-wise here is pretty easy. The carbonyl just pulls electrons out of that double bond and now builds a positive charge down to this far carbon. So I think you can see what's going to happen in our reaction is the negative center on the diene is going to look for that positive center on the dienophile. And that's exactly what we're going to look for in a little bit. Now, the other thing that we have to worry about is the stereochemistry. Now, the stereochemistry means essentially what's the relationship of the various groups around the ring in terms of being cis or trans to one another. And the key thing is in the dienophile. I mean, you start off with an alkene. Alkene you'll have it be a particular isomer, E or Z, depending upon the substituents. And in this particular case, I have A and B cis to each other, D and C cis to each other. Well, the way the reaction works, we're just drawing new bonds from this carbon to that carbon, from this carbon to that carbon. The relationship between A, B, C, and D don't change. So if A and B are cis in the alkene, they're going to be cis in the product, except now cis on the side of a ring, and C and D will be on the opposite side. So C and D will be trans to A and B, and cis to each other, just like they are in the reactant. So cis in the alkene, cis in the cyclohexene. Same thing for trans. Trans gives trans. Now, so in this particular case down here, we have our diene has no substituents. Our dienophile has a carbonyl, good electron withdrawing group, and it happens to be trans to this methyl. And in the product, it's also going to be trans to the methyl. You can't go from trans to cis. You always go from trans to trans. So this is a simple enough problem. What's the reactance of this Diels Alder? So again, let me pause the quiz a little bit. This is question 3 down below. See if you can answer it. Okay, so how do we solve this? Well, first of all, we want to figure out what are the new bonds. Well, when the diene reacts, the two original double bonds go away, and you get a new double bond between the two original double bonds. So here's the double bond, which in what was the diene. And so that means that the original double bonds were here and here, which means this is a new bond and this is a new bond. So the dienophile has the methyl and the cyanide on it, and the diene itself is simply butadiene. Now the methyl and the cyanide are trans in the product, so that means they have to be trans in the reactant. So butadiene is D down here, and the trans one is this one here, so the answer has to be D. That's pretty simple. Okay, it gets more complicated because now we have to worry about the substituents on the diene. Now, normally when you draw a diene, you draw it out like in this particular direction with with kind of what we call transoid orientation, or sigma trans around that sigma bond. Now I'm going to label these positions. So if this substituent here, this what I call the T position, is because this substituent is trans to the other double bond. This is the T position because this is trans to the other double bond. This is the C position because this is cis to the other double bond. This is C because it's cis. And these ones in here we'll just call the M position for middle. Now when you twist that S trans configuration around to give the S cis, which we need for the reaction, now these positions which were T here become T here. They're the outside positions in this kind of folded conformation of the diene, and the C positions run into each other. And of course, if the C positions are too big, you can't form this conformation, and the reaction won't occur. Now, once you do the reaction, what happens? Vision the dienophile coming up from behind, and what it does, it pushes the C's up, and if the C's get pushed up, the T's have to go down. So when you do the reaction, and if you're bringing this up from the bottom, the C's get pushed up and the T's turn down. And so the key thing is the T positions become cis to each other, and the C positions become cis to each other. So T is trans to the other double bond, C is cis to the other double bond, M is the middle position. In the product, the T positions will be cis on one side of the ring, the C positions will be cis on the other side. The M groups will be on the double bond. So this is the pattern, and it sounds complex, but when you actually start doing it, it's not bad. So let's see if we can actually do. Well, here's a picture trying to show you why why this works, and you bring the diene from the bottom, which means that your C's will be on top and your T's will be down, and the C's will be cis, the T's will be cis. So there's the basic picture of the molecule. Okay, of course it folds into a chair, and one C will become equatorial, one axial, same thing with the T's. And it's probably best not even to worry about the chair at these things. It'll just confuse things more. Okay, so let's try to do one of these problems. So again, pause the video. This is a problem down below. See if you can figure it out. And what you want to do is label everything like the little drawing down here, and you should be able to figure it out. Okay, let's go through it. So the first thing I'm going to do is I'm going to redraw this in the cissoid configuration, and all I've done is rotate around this central single bond between the two double bonds. This is now the cissoid configuration, ready to do the reaction, and those are going to be the new bonds. And the key thing is these groups which are pointing out, these are the so-called T positions. They must be cis in the product, and so the ethyl and the methyl must be cis. So if you look at this particular one, well, here the ethyl and the methyl, they're cis here, they're cis there. Oh, they're cis there, but here they're trans. So D is out, okay, and that's one factor. But then we have to look at the dienophile, and the acyl group here is trans to the methyl. So let's look here. Well, here they're cis, that's no good. Here they're cis, that's no good. This one down here, on the other hand, they're cis. So C is just fine. So it's C. Actually, A and B are the same thing, aren't they? Well, no, they're not. Oh, the methyl moved. Ah, of course, the methyl moved. But silly me. They're different, but they're both wrong. Anyway, but this one's good. Okay, C is good. So that must be trans, and so that gives you molecule C. Okay. So, if you think about this diene and this dienophile, there's 8 different possible products. How can I get to 8? Well, you think of you got your diene and you got your dienophile. Well, basically, let's consider that the dienophile comes in from the bottom. Well, that carbonyl could essentially be in any of the 4 corners, bringing it in from the bottom. In other words, it could be on the top to the left, it could be the top to the right, it could be the bottom to the left, the bottom to the right. That's 4 possibilities coming in from the bottom. Why is the bottom significant? Well, you can bring it in from the top as well, but that gives you an enantiomer. That essentially is a mirror image, because you think of the diene as having a mirror image, and you're bringing the dienophile in from one side of the mirror or the other. So there are 8 possible products, and here I've drawn them all out. So in this particular case, I've simply drawn out 8 possible products. So here we're cis next to each other, they're trans next to each other, one up, one down, one up, one down, and then the other orientation is the carbonyls away from the methyl, and again there's one up, one down, one up, one down, depending on whether or not they're cis or trans to the original methyl group. So there's 8 possibilities. Now the 4 on the left are enantiomers of the 4 on the right. So A and E are enantiomers. So this is enantiomers. They're opposite chirality. What about these two? these two have different stereochemistries. The groups are in the same place, but there's one, the stereochemistry of one of them has been changed. So those are diastereomers from respect to each other. There's the diastereomer, of course, is a stereoisomer, which is not an enantiomer. So this actually, I guess I should say diastereomer to be more specific. They are stereoisomers, but more specifically, they're diastereomers. And then, then we compare A and C. What's the relationship between A and C? Well, this is different regiochemistry. So they're constitutional isomers. The carbonyl is simply at a different place. So that's a constitutional isomer. So there's three kinds of isomers here. There's enantiomers, the diastereomers, and there's constitutional isomers. And if we sort these all out, we would really be doing something. And what would be really great is if you could do the reaction and know which one of these you're going to get. And it turns out you can do that. And that's kind of the amazing thing about the Diels Alder reaction. And the way we're going to do it, of course, is we're going to take advantage of this charge model that we hinted at before. When you add an electron donating group, you get a buildup of negative charge here at this bottom carbon. So electron donor groups get negative charge to this carbon atom. And the other hand, you have electron withdrawing groups, you'd pull electrons out of the bottom carbon here, which means that when you put these two together, you can tell exactly which way it wants to go. And so it's pretty simple. You want delta minus and delta plus to line up, which means that if you have a electron donating group on one end of the diene, the electron withdrawing group wants to be next to it. So this is what we call the 1,2 to one another. So they want to be 1,2. And on the other hand, if you have electron donating group there, then the carbonyl wants to be 1,4 away from it. So regiochemistry is 1,2 or 1,4. Now, if you have multiple substituents around here, I mean, maybe you had one on the other end too. Well, then you can't tell. It's just a mix. It's just a mix-up. But if you have one substituent in one position and then another one in the 3 position, then they would both dump a negative charge into this carbon, and that would be great. So 2 donor groups and one at the end, one over here would be perfect. Other patterns could be unpredictable. But if you can do it, 1,2 and 1,4 is the relationship between the electron donating groups and the electron withdrawing groups. This is kind of similar to the rules we did for aromatic chemistry, but the root of the rule is really very different. So 1,2 or 1,4. So which means when you do this, if you bring it back this way, of course, the charges are simply not working, and so you don't do this configuration. You don't do this configuration. 1,3 just doesn't line up. Okay, so which of these would be the product? Again, pause this and see if you can figure it out. So in this case, our electron donating group is this methyl, okay, and the cyano group is the electron withdrawing group. So which one are we going to get? And so you want to consider the charge relationship, and then of course you have to take account of the fact that this is the cis isomer. So pause the video, figure it out. Okay, unpause. Oh well, I thought there was an answer here. We have to figure out the answer. Well, we know that the cyano group wants to be next to the methyl. It wants to be 1,2, and so cyano group next to methyl is either B or D. And how can we tell the difference between B and D? Well, in B and D, the cyano group is cis to this other methyl, and here is trans to the other methyl. But in the reactant, it's cis, so it has to be B. So the answer is B. And again, this is kind of powerful because, of all these various isomers, you just get this one. Okay, so that is going to rule out all 4 of these down here. So we've done a whole lot. So now what we like to do is to see if we can figure out what's going up here. In particular, we're going to worry about A versus B. So we're going to worry about which of the diastereomers we're going to get now. So how do we do that? Well, this is essentially, when you get down to it, is this carbonyl pointing away, or is it pointing up? Is it pointing up, or is it pointing down relative to the say the T positions over here? So is the carbonyl cis to the T position, or is it trans to the T position? Is the way you can think about it. We call the cis one endo. We call the trans one exo. Now, how do we figure this out? Well, again, we go back to our orbitals. If you look at this carbonyl here, this carbonyl is actually a diene as well if we count the carbon-oxygen double bond as another double bond. And the orbitals of this, when we normally just think about the double bonds of the carbon-carbon part, but let's extend it out into the CO. Now the coefficients wouldn't be the same, but nevertheless it's extended out into the CO. So that means this highest occupied orbital actually it spreads out onto the carbon monoxide, or the carbon monoxide, the CO, the carbonyl, not carbon monoxide, carbonyl a bit. And so the way to look upon this is that this donor group has some stuff sticking underneath here. Or if you turn around the other direction, as something sticking out here. Now, if we do this one, the orbital is extended underneath, and it can also interact with the backside of the diene. So these 4 orbitals will interact with this better than these 4 orbitals will interact here, because they're right underneath each other. They're face to face. They're flat to flat. So endo has a better overlap between the entire HOMO and the LUMO. Exo has a poorer overlap between the entire HOMO and the LUMO. So it's this orientation of the pi system from the electron withdrawing group placed underneath the diene, which makes it better. So endo is favored from this transition state, which is this. It's essentially a kinetic argument. Is it kinetically, it's better to come underneath. And so that turns out to be the governing factor, and you tend to get endo. Endo wins. Endo is favored. And so when you work this out, again, here we're just setting up our interaction. It'll be with the carbonyl underneath, okay, which will give us the cis carbonyl. The electron withdrawing group will be cis to the T position. If there's an electron donating group there, it'll be there. If it's a hydrogen, of course it's just a hydrogen. But anyway, it'll be cis to the T group, and that's the endo isomer. And it actually, again, it works and is quite good in making predictions. So the electron withdrawing group will be cis to the T groups. So here, let's do an example. Now this is a strange diene because it's bound with this oxygen, which of course makes it a very good diene because it's held in the cis configuration. And so again, this oxygen is a very good electron donating group, and it's on the N carbons. Now that means there's no directional preference. There's no regiochemistry here because the carbonyl can go either up or down because this molecule is symmetric. But is it endo or exo? And so it's going to go underneath, and these are the 2 possibilities: underneath, which is this one drawn like the way the product would be, but this is what the transition state would be. And this is indeed the favorable process right here. Okay, so again, let's look at this particular pair. Now here, again, pause and work it out below. How are we going to do this? Well, the thing to think about here is, again, we want the carbonyl next to the methyl group. So that's the regiochemistry. So we're going to look at this right here. These are the new bonds we're finding. So the carbonyl is away from the methyl group. That doesn't work. Carbonyl is away from the methyl group. That doesn't work. But here the carbonyl is next to the methyl. Here the carbonyl is next to the methyl. The carbonyl wants to be cis to the T groups. The T group is the methyl. So cis to the methyl, that's C. Okay. So that works. And then this other methyl, this one up here, is this methyl, and it's trans in the dienophile. So carbonyl is trans to the methyl. So the right-hand side here is this piece right there. Its regiochemistry is correct because the carbonyl is next to the methyl of the diene, and the stereochemistry is the right diastereomer because it's cis to the methyl. So C is the correct answer. Very good. And let's do one more example. Here is a great, this is a really good dienophile. Again, there's no directionality because it's symmetrical, but this has 2 carbonyls on it. So this is really very reactive. And this is a very good donor, the oxygen lone pairs. And again, it's on both, so there's no directionality. So this is a easy reaction to do. It's a good diene and a good dienophile. And when they come together, what's the 2 possibilities, A or B? Well, let me ask 2 questions. Which would be the thermodynamic product? Well, that's interesting. Well, the thermodynamic product, if you draw them out, the exo looks much better. There's obviously less steric hindrance in the exo, than there is in the endo. So the exo is the thermodynamically best product. But which product would you actually expect to get? Well, you expect to get the endo. So this is one of the cases where the kinetic product, which is the endo one, because of that better overlap of orbitals as the reaction is forming, wins. So this is one of these cases where we talk about the kinetic product winning over the thermodynamic product. Very good. So we've crossed out these two. Now all we have is the pair of enantiomers. Now, what can you say about a pair of enantiomers? If you just use the two molecules that we've been talking about, you're doomed. There's no way you can select for an enantiomer, right? Because you can't get chiral, you can't get a single chiral compound out of achiral reactants. So we have to introduce chirality into the system some way. Well, one way to do this is to be sneaky. So we're going to be sneaky. It turns out that here's an electron withdrawing groups. How could you make an electron withdrawing group better than it is? Well, what you could do is you could protonate the carbonyl. Well, protonation isn't a very good way to do it, but adding a Lewis acid is. Add some BF3 to the reactant, or some aluminum trichloride. That would coordinate the lone pair up here, polarize this whole thing, making the carbon down here more positive than it would be on its own. And so with the boron up there, the boron will take on a negative charge. This will take on a delta positive charge. So what you've done is you've made the dienophile better. And when the reaction is all done, you lose your BF3, so it's a catalyst to make it faster. Well, it still doesn't introduce chirality, but it's going to get us there. So this reaction becomes faster with catalyst. It also makes the endo thing better because it makes the electron scepter better, which means that the interaction with the orbitals of the diene in the transition state are better. So that's pretty good. Now, so if you do this with BF3, you get a 50-50 ratio. But here's the trick. Use a chiral catalyst. Use a chiral Lewis acid. And if you use a chiral Lewis acid, then the ratio doesn't have to be 50-50 because the chiral catalyst can promote one orientation better than the other. And here, this was done in a class experiment by Professor Corey at Harvard, where he devised this boron compound, which is just inherently chiral, and it's got a beautiful chiral center up there, and it is such that the dienophile shown here will coordinate to the boron, and basically it wants to form it forms a kind of a it takes a particular orientation because of that phenyl ring behind it, which means it blocks one side of the dienophile, which means the cyclopentadiene, the diene, can only come in from one direction. It wants to be endo, but it doesn't have a choice of which side of the dienophile it attacks. So when you just do it, the ratio isn't 50-50. In fact, it's 99-1. And so this is now selecting out a particular enantiomer of the entire thing. So when you're done, and you've done the whole thing, you get one molecule out of the possible 8. And that's what makes the Diels Alder reaction so very, very powerful, is that if you apply all these rules together, you can say which molecule that you're actually going to get. Now, we're not going to worry about the chirality one, because predicting which enantiomer you're going to get is essentially impossible for amateurs like us. I couldn't do it. I certainly don't expect you to do it. I want you to know the concept of using a chiral catalyst, but we're not going to do any predictions. So anyway, that set up the whole Diels Alder reaction. It's pretty complicated. It's a bit long, but it's really good chemistry, and we're going to have some fun with it.